since two days. Let me share the PPT. Okay. So we started since two days, and two lectures are over on compiler design. This is the third lecture. In the yesterday lecture, what we covered actually, we started realizing the work to know the work of each and every phase of the compiler. Okay, in that we took an example, realize their work, and that was not exactly covered because of the lack of because of the time constraint. Okay, so where we left yesterday, there only we will start from there. Okay, so let me recap on that. That we started realizing the work of each and every phase of the compiler. Okay, we came across what is lexical analyzer, and we took one example to realize how it perform tokenization. And then what is the role of syntax analyzer, how it impose grammatical structure in order to identify whether a particular sentence is grammatically correct or not. Then we came across we realized the role of semantic analyzer, how it perform type checking, and whether a variable is declared or not declared, how any redundancy declaration is there. Okay, these are the things we came across. Now, finally, what we came to know that lexical analyzer it collects, I mean, creates token and store them in the symbol table. And this syntax analyzer collect all the tokens from the symbol table and impose a grammatical structure on them. That is called as context-free grammar to realize to know whether the syntax is, I mean, the structure of the sentence is correct or not, or the the grammatically the sentence is correct or not. Then it produces a parse tree as an output. This parse tree is passed through the syntax semantic analyzer as an input. The semantic analyzer performs some kind of checks, and then it produces another kind of parse tree that is called as abstract parse tree. This abstract parse tree is now is passed as an input to the intermediate code generation. So here we need to start. We need to realize what exactly the intermediate code generation does. Okay. Okay. I made it full screen now. Okay. Here you see the intermediate code generation. This is the fourth phase of compiler. Okay. It generate machine independent intermediate code. Machine independent in the sense which is not dependent on the underlying architecture of the machine. Okay, like the which does not depend on the number of registers present in your system. General purpose registers, what is the instruction set, what is the addressing mode, and what is the operating system running. All these things it does not bother. Okay, rather, irrespective of the machine architecture, this code runs smoothly. Okay, in any system. That is why it is called as in machine independent code or machine independent intermediate code. So the role of intermediate code generation is generator is to break the entire source code into a different format, different but particular format, that is called as three address code. Okay, so you can see in the second line, the intermediate code generation phase of a compiler usually convert the source code into an intermediate representation known as IR. Okay, and one of the most commonly used or popular IR, I mean intermediate code generation, intermediate representation is three address code. Three address code means that code, it is a code where maximum, okay, maximum three operands can be placed. So you can understand now, maximum three operand. Okay, so there may be only one operand, there may be two operands there, but maximum there can be three operands, not beyond that. Okay, so such type of code or representation is called as three address code. Okay, you can see in the right hand side of the PPT. Okay, and I try to understand or try to recall that the abstract syntax tree, what already produced by the semantic analyzer, that is now passed as an input to the intermediate code generation. That is ID1 equals to ID2 plus into ID3, on the other hand into real 60. This is the abstract syntax tree. Okay, this syntax tree is now act as an input to the intermediate code generator. The intermediate code generator, what it does, it breaks the entire syntax tree, or it breaks the entire code into three address format. Okay, how it does? First, it allocate the into real. Into real is an operator, and 60 is an operand. So that together, how many operands? How many operands are there? Only one operand, that is 60. And how many operators? There are two one copy operator, another one is conversion operator, implicit operator, that is called as into real. So first of all, what it does, it converts the value 60, integer value 60 into real. Then it will place that result in the temporary register. The temp1 is nothing but the temporaries. Okay, so it is in this particular code, the compiler allocate number of temporaries to hold the value. Okay, temporaries in the sense these are the, you can say that these are the temporary registers. Okay, just they hold the value for what calculation purpose. Okay, for they hold the value only for sometimes or few times. Yeah, for sometimes. Once the memory allocation occur, these temporaries will be empty. Okay, or you may say they will be die. Okay, so in this particular phase, intermediate code generator, it allocate number of temporaries to hold different values. So you can see it how it breaks. First of all, it assign the real value 60. Okay, real value in the sense, why I am saying real value, because we already convert that value by using an operator called as into real. Okay, previously it was 60, now it is converted to as into real operator has been assigned. Okay, and the role of into real operator is to convert the integer to real. The integer number 60 is now converted into real, that is 60.0. Okay, so that is why. So first what it does, now you can see it allocates the real value 60 to the temporary temp1. Okay, next what it does, yeah, in temporary 2, it allocates ID3 into ID3 means identifier 3 into that piece of code. You can analyze ID3 into temp1. Temp1 means it holds the real value of 60. Okay, real number 60. Okay, so now temp2 is another or new temporary which holds ID3 into temp. Now, in this code, in this particular line, how many operands are there? 3 operands. One is temp2, second one is ID3, and third one is temp1. Okay. Now, you cannot allocate another things, another operand here or any other operator here. This line is complete. Okay. Maximum 3 operands can be there. Okay. So now, next, another temporary is has been assigned, that is called as temp3. Temp3 is holding the result of the temp1, temp1 as well as temp2. Okay, I mean it holds the result of ID2 plus temp2. Okay, temp3 is equals to ID2 in the sense identifier 2 plus what is temp2? Temp2 is holding ID3 into temp1. What is temp1? Temp1 is holding into real 60. Okay. So in this next, finally everything is placed in temp3. But temp3 you cannot store the data in temp3 for permanently. Okay, because that is one temporary register, or simply you can say temporary variable. You cannot store the data there permanently. You need to place the data. You need to place the final result in the memory. So for that, what is the memory? Memory variable here is ID1. Okay, ID1 is the real variable which holds everything. because we started from position. Position equals to initial plus rate into 60. So the left hand side variable is position. Now that variable is renamed as I mean the token type of that variable is identifier 1. So that is going to hold the everything which is present in the right hand side. Everything will be calculated and the result will place in position. That is the thing. Okay, so the same thing, but it divides the entire code in a specific format. Okay, that is called as intermediate representation, or you may say the example you may take it as a three address code. Okay, three address code is one of the best format that has been that has been given by this intermediate code generator. Okay, so every code need to be converted into three address form, three address code form, where maximum three operands can be there. You can see in these 4 lines, there in the first line there are only 2 operands. In the second line consists 3 operands. Third line consists 3 operands, whereas last line consists only 2 operands. One is the source, another one is the source, other one is the destination. Okay, so here the value of destination get copied into source. What is source? ID1. And what is destination variable? That is temp3. Right? Very clear. Next, once we now this is the role of the fourth phase of compiler, that is called as intermediate code generator. Now let us realize the next phase. What is the next phase? Can you tell? The next phase of the compiler is code optimization. Okay, code optimization, and as I said before, code optimization is of 2 types. So one is machine dependent code optimization, other one is machine independent code optimization. Machine independent code optimization normally takes place in this time, that is just before the code generation phase and immediately after the intermediate code generator. You can say, sir, the code optimization or the machine independent code optimization takes place immediately after the intermediate code generator. And machine dependent code optimization takes place just after the final phase. I mean, just after the code generation phase. Okay. So now we are realizing the work of each and every phase briefly with an example. We are just trying to understand. So we'll not discuss much things in code optimization, because the specific topic unit maybe unit 5 we'll discuss that. Okay. Now, just try to understand. Here easily you can understand, but we will not have a chance to cover with multiple examples. But whatever examples is present, we can easily understand what is the role of the phase code optimizer. Okay. Here you read the few functions of code optimizer. It improves the execution speed of the program. It reduces memory uses. It removes redundant code. I told you, yesterday. Let us take one example that within a single scope, you mistakenly, okay, so let us say that you are the beginner of the beginner to the programming language, okay, then you can do mistake. Without mistake, you can't learn the things. I must suggest you that you should do the mistake so that you can learn from that mistake. Okay, you can learn because your system is there in front of you. It will help you. You try to do the same thing multiple times. Once error occur, don't leave the system and go away. You keep doing the things. Try to understand what error the system is saying, whether it is a syntax error, whether it is an exception or some other kind of error, where you forgot to close the bracket. Open bracket is there, but you forgot to close the bracket. Then the program is, is not complete. There you have to, so you have to learn and do mistake and learn from that mistake, particularly in coding. Now code optimizer. In code optimizers, as we discussed, it improves the speed of the program execution. Reduces the memory uses, as well as it remove the redundant code. If you declare mistakenly one variable two times, that is called as a duplicate variable, duplicate declaration, a redundant declaration. Everything is correct logically. I mean, for lexical analyzer, there will be no problem if the variable is declared for two or three times. For syntax analyzer, there it won't catch that error if the variable is declared for two or three times. Because syntax analyzer, it will focus on the grammatical part of the programming construct or programming structure. So it will not tell you why you kept one statement two times or three times. So that can be catched by this code optimizer. If one variable within the same scope is declared two times, that will be called as a redundant duplicacy. That duplicacy will be removed by this code optimizer. Okay. Okay, now come to this example, the same example. Now what output you got? You got temp1 equals to into real 60, temp2 equals to id3 into temp1, and temp3 equals to id2 plus temp1, and id1 equals to temp3. Okay, this is the output of intermediate code generator. This output is now act as input to the code optimizer. And code optimizer, what is the role? It will minimize the code. It will minimize in the sense what? It will optimize the code. Instead of maintaining duplicacy and writing more code, I mean complex code, it will try to shorten the code so that the code can occupy less memory, redundancy can be eliminated, and the code can be improved such a way that it can run faster, okay, comparing to the previous version. That is the objective of your code optimizer, right? You can see those 4 lines of code, how it is minimized without changing the meaning of the program, without changing the meaning of the program, without losing the information, without losing the data. Okay, the same 4 lines of code is now reduced to 2 lines, and the same format is also maintained. 3 address code is also maintained. What is the purpose? What is the 3 address code? In 3 address code, maximum 3 operands can be there. The same thing is present here. So here temp1, first of all, it convert into real 60 means the operator is there to convert 60 into 60.0. So this the code optimizer, what it does, it remove, it directly convert through that operator, it directly convert the integer value 60 to 60.0. Okay, now after that, temp1, everything was placed in temp1. Now temp1 becomes 60.0. Temp1 becomes 60.0. Okay, now temp1 equals to id3 into 60.0. One line statement is over. Next, temp3 equals to id2 plus temp2. Okay, id2 plus temp2. What is id1? id1 equals to id2 plus temp1, because in temp1 you kept id3 into 60.0. Okay, so no need to keep. Now the second statement. Okay, what is temp2 actually? Now temp2 is nothing but temp1, because in temp2 you kept id3. Temp1 already eliminated because that value directly converted 60 to 60.0. So that it becomes a real-time constant. So that is directly placed in placed along with id3. id3 into 60.0, total value is kept newly in temp1. Next, id1 is equals to id2. id2 is an identifier. id2 plus temp1. So the entire 4 lines of code. So you see both the lines are 3 address code. I mean 3 operands are there in both the lines. So both now those 4 lines is converted into 2 lines. That is called as this is the one snapshot of code optimization. Only small example we took to understand, okay, to understand what is code optimization. Okay, what is the role of code optimization? When we go into that topic, no number of examples are there. This is not only the role, number of from different perspective, from different angles, the number of examples are there, and very interesting. This subject, this particular unit is very interesting. Okay, that we will discuss, no problem. Next, let us realize the role of code generator. Once the code is optimized, this optimized code act as an input to the code generation. Okay, or you may say code generator, code generation, or you may say code generator, no problem. Okay, so this code generator phase, it takes code optimized code. Remember, optimized code as an input, and it perform register allocation along with the instruction set present in the system. So it perform register allocation, okay, to for the register allocation to perform real time calculation and store the value in the memory. So it produces final machine code. How the machine code can come? The machine code, it comes in terms of, first of all, it will convert into the entire code will be converted into assembly code. This assembly code is nothing but one output of code generator, or sometimes, okay, some code generator, okay, where it perform register allocation. So here actually registers, instead of temporary, actually registers are used to store the value for temporary purpose until the entire result placed in the memory. Okay, so how it perform register allocation? Using the instruction, okay, that is move id3 comma r2. Move f, why f is given? That is because in this expression 60.0 is nothing but a real time number. Okay, I mean real number, that is. And I, as I said, that position, initial and rate, all others are already taken as a floating point number. So as the entire expression is in the form of floating point numbers, that means the result in the form of floating point number or real number. That is why instead of move f is there. That instruction f, move f indicates floating point number, or that value, the which is I mean which this instruction is dealing with, the values are in real number or floating point number. Okay, ultimately you can say, as this instruction, as this expression holds floating point numbers, okay, here all the instruction will automatically add f into the original instruction. F indicates that the numbers are floating point numbers. I mean, here you try to understand, move f id3 comma r2. That means what is there in id3? id3 first you store in r2, then multiply, okay, mulf, multiply f 60.0 comma r2. What is the expression? Temp1 equals to id3 into 60.0. I mean id3 is nothing but one identifier, where which is getting multiplied with 60.0. So first store that identifier in a register, then multiply the value 60.0 in that id with the id3. The entire value you keep in somewhere, where you are keeping, you are multiplying and storing the value in R2. So try to understand. First in R2, store ID3. Then what is the next part? 60 is multiplied with ID3. Now ID3 is present in register 2. Now multiply 60. The entire value will be in register 2 only. That is the second line. Okay. Then third line, move F ID2 into R1. Okay. ID2 into R1. R1 means a new register. Okay. Put ID2 in R1, then add what you are adding. Add the value of R2 in R1. Okay. Whatever what is the present in R1 and what you already found in R2, now add the value of R2 with R1 and hold the and store the result again in R1. Okay. Now let us say I kept 5 in R1. Now I am adding 6 in R1. Total will be 11. That 11 will be in the same place R1. R1 is nothing but the room or the register which is holding. Just imagine it is a room where two variables, previously one variable was there. Now second variable is added, or the result is also placed in the same room. Similarly. Okay. Now R1 is holding the entire result. But my question is, can we hold the result permanently in R1? No. That is why we need a place called as memory to store that value. Because registers are very limited in the system. Okay, very limited. And these registers, but so that is why, and one process or program execute, the registers are get vacant and they allocate to another program or another process. So that is the policy. Okay, so that is why we need a memory to store the entire result which is present in R1. So move F R1 comma ID1. What is ID1? Finally, you are storing the result where? In position, the variable position. What is the ultimate name of position? The ultimate name of position is identifier 1. So identifier 1 is nothing but the memory. I mean the placeholder of the memory where you are putting the enter. Enter result in the sense initial plus rate into 60.0 or into 60. The total right side will calculate and placed in left hand side. What is that left hand side? Left hand side is position. This position, the ultimate name of position is ID. Okay, is that clear? So this is the role of code generator. So in this class, what we learn since yesterday we started to realize the role of each and every phase of the compiler with the help of an example. And today we completed. Okay. Initially, we observe how lexical analyzer reads the source code, how it identifies the token for each and every lexeme or word, how it places them in the symbol table, then how lexical syntax analyzer collects them and impose one grammatical structure to identify whether the sentence is grammatically correct or not. Then how it produces the, what is the output of syntax analyzer? The output of syntax analyzer is a syntax tree. The syntax tree is again passes to as an input to the semantic analyzer. It performs certain checks and finally it produces abstract syntax tree. This abstract syntax tree is passed as an input to the intermediate code generator. It converts the entire source code into intermediate representation. The specific type is 3 address code. This 3 address code is again passed as an input to the code optimizer. It eliminated redundancy, duplicacy, and it fasten the code. Okay, it is speed up the code. Okay, by optimizing the code. Okay, it is the major focus of code optimizer is to is to see how the memory uses will be less and how the speed of the program can be improved. And then now we have seen that finally the code optimizer phase produces the optimized code, and this optimized code is passes to the code generator, and the code generator perform register allocation. Okay, and it produces executable instruction, okay, in the form of assembly code. And finally this assembly code, when it passes through the assembler, binary code get generated 0 and 1. Okay. Now you see the other phases, the role of symbol table and error handler. You see position symbol table, it stores different types of things, variable names, data types, where it is stored in the memory, I mean memory location, what is the scope. Okay, suppose in function one variable is declared, in function two another variable declared, so their scopes are different. Okay, so all the information stored in the symbol table. You see, when the initially the lexical analyzer breaks the entire source code, position, initial rate, these all are what identifiers. Identifier one, identifier two, identifier three, like that it stores. It also what is the data type of position, what is the data type of initial, what is the where is the memory location, what is their scope. Every details it stores in the symbol table. That is one data structure. Now, error handler, yeah, there are many types of error. Most of the errors are normally identified by lexical phase, I mean lexical analyzer, syntax analyzer, and semantic analyzer. In the rest of in the intermediate code generation, code optimizer, and code generation phase, the errors are almost zero, because these are the three the upper layer of the compiler. Okay, upper layer of the compiler, these three phases, these three phases normally identify the error. Once the program passes through semantic analyzer, the error is almost rare, almost zero. Okay, because that is very close. The once the semantic analyzer produces abstract syntax tree, and abstract syntax tree passes through the intermediate code generator. Once intermediate code is created, intermediate code is very close to the target code, so that is why the error is almost zero there. Okay, diagrammatically it is shown because the error is almost zero, rare case. That is why this phase is diagrammatically associated with all the phases. But logically, if you see, the errors are identified only by the first upper three phases. Okay. So this is the brief discussion about, brief discussion we took about to learn or to realize the role of each and every phase of compiler. Now, from next class onwards, we will be discussing unit 2. Okay, this is all about your unit 1. Unit 2 start from lexical analyzer. Unit 3 start from syntax analyzer. Like that, we will discuss. Okay, in-depth study of each and every phase of the compiler. Okay, so here you can see unit 2 lexical analyzer. You just note down the topic. Okay, here we'll start in the next from the next class onwards. Okay, so I hope everything is, I made it very clear and repeatedly said many things, and I hope it is very clear to you. Okay, and in the consequence, yeah, rest of the classes will have more interaction. Will be because the subject is very interesting. Okay, we'll be knowing the subject in depth, and we'll spend some time on this. A very interesting subject. I can suggest you that you'll be once you concentrate, you'll definitely you'll do very good in compiler design. Okay, and you can be a master in compiler design. Okay, so thank you. This is the in the next class we will discuss from the second unit onwards. Okay, thank you all. Have a nice day. Hmm? Thank you once again.